Okay, I think we can begin now. Okay, so first of all, I got this little bit of a better angle here, I think. Wow, why is this delayed? Yeah, so welcome to the stream. For some reason, the video on my OBS is like delayed, which looks very weird for me, but I hope everyone's doing okay. So yeah, we'll just be doing some exercises here. Hopefully I'll get my mind off everything, and we'll just talk about math and have a good 4-hour session here. So, um, yeah, basically just try not to be too sad and think about other things. So, okay, yeah, the video seems good. Okay, yeah, so I'm trying to get the angle here a little bit better. I'm trying to do something a little bit different. Oh, you can like see oh, everything froze. Okay. Okay, now it's good. Okay. Yeah, the only problem is you can like see the screen in the middle of the whiteboard here, which looks a little weird. But yeah, so have we posted any exercises in the Wednesday section yet? Let me take a look in there. And if we haven't, I suggest we can so far.
I can what?
Mom, stop. Close it.
Oh, you were talking to me.
I literally just told her like 2 seconds ago. Yeah, so everyone here is a little bit out of it still, so unfortunately. But yeah. Yeah, I could try the chalkboards, yeah. Thank you, Zach. Right. We could switch to chalkboards and that would always solve all of our issues, right? Yeah, so just looking for some interesting math problems to do. Otherwise, I was thinking I would go over a little bit of like complex analysis, something in that ballpark. Yeah, so I think that's probably the next direction I want to go in. Yeah, Zach's definitely not biased, of course. We all know that. So maybe let me just give you like a little bit of an informal introduction to complex analysis, if there's no questions initially. Okay, so, and also maybe I'll talk for maybe like an hour or two and then we'll take a break. Also, I need to charge my laptop at some point or else it'll probably die. So, but yeah, so what is complex analysis? What is a complex number? What is the purpose of the complex numbers? We all know the real numbers, right? So what would the, yeah, what would the need of this extra dimension be, right? So we're all familiar with the normal real numbers, right? Which we usually denote with this like blackboard R, right? So these are our normal numbers like 0, 1, 2, everything in between. So we have like 0.5 here. Can you teach me fractions? Yeah, so the real numbers, they include all the fractions, right? But they also include all of the irrational numbers as well. So there's, there's some number, I think it's somewhere around here. It's like the square root of 2 over 2, right? This is an irrational number. This is a number that we can't write as a fraction. So we can prove that that's not a fraction, right? So real number basically contains all of these integers as well as all of the fractions and as well as all of the wholes in all of the fractions, which basically includes all of these irrational numbers, and sometimes we have like transcendental numbers as well, right? Numbers that don't even satisfy any polynomial equation, but are somehow needed to like fill in the holes in between all of these rational numbers, right? So yeah, what is the need of the complex numbers? So essentially, yeah, we're thinking of, I guess, we already needed to include extra numbers to include things like solutions to x squared equals 2, things like that, that don't have any rational roots. So similarly, mathematicians try to give things solutions that maybe don't initially have solutions in some underlying field. So, here we're adding a square root of 2. If we add a square root of -1, that's basically how we get to complex numbers, right? So we're adding a root to some polynomial. It just happens that x squared equals 2 doesn't have a root in the rational numbers, and also x squared equals -1 also has no root, has no solutions in real numbers. Okay. Can everybody see this? Is this angle okay? Is the lighting okay? Everything? Just testing out some some new stuff, so hopefully everything looks okay. But yeah, so I mean that's kind of like a reoccurring story in math. We're looking at polynomials and we're progressively adding more and more roots to some of them. So like I said, x squared equals 2 has no roots in the rational numbers, so we can sort of like create a new number that is a root of this. And similarly, for x squared equals -1, it doesn't have a solution for real numbers because when we square any number, it's positive, right? Any real number we squared, it's positive. So this has no solutions in the real numbers, but we can sort of give it a solution, and we end up actually getting 2 solutions. So we get an I and a -I, which are both their solutions to this. So I squared is -1, but also -I squared is also -1. Okay, so we basically add this new number to our number system called I. And we want to sort of include more stuff as well, right? We don't just want I and -I, but we want to be able to add these numbers with real numbers. So we want to have some sort of closure under addition. There should be a way to describe like 1 plus I, for example. So not only are we adding I to the number system and -I, but also like 1 plus I, 2 plus I, 3 plus I, pi plus I, pi plus pi times I, right? So any a plus bi, where a and b are real numbers, a and b are real numbers. This is how we describe, this is sort of like, you can think of it as we took the real numbers and then we added an I, but I also want it to be a vector space. I want it to be closed under multiplication by a real number. So in order to have that property, we need to be able to multiply I by any real number. So I should be able to add any real number plus any real number times I. And if I take all of these possibilities, that's the whole number system. So I'm basically adding a new dimension to the number system, some number here I, and -I, of course, and also every other scalar multiple of I, and I can add. So basically, I'm getting an entire two-dimensional plane of numbers. For A and B are 2 real numbers, and they basically describe the 2 real dimensions. So one way you could say that is that the complex numbers are a 2-dimensional vector space over the real numbers. So we talked about, if anybody was watching the linear algebra videos, we talked about how every vector space, if it's finite dimensional, it has some dimension. You can show that complex numbers are finite dimensional, so they have some dimension. The dimension just happens to be 2. You could, of course, create vector spaces over the real numbers of any dimension, but this one is special in particular because it has a multiplication. So we can actually take two of the numbers of this type and multiply them together, and we get another number of this type. Yeah. So does anybody have any questions about complex numbers, or even better, does anybody have any problems we could look at with complex numbers? Or anything in general. But yeah, this is your very short, ultra brief, informal introduction to this stuff, but I'll do a more formal introduction on Friday. So, okay, not getting much from the chat, so might have to go off on my own. It's gonna be a long 4 hours. Okay, what else should I say? Let's see. I guess we could talk about multiplication in the complex numbers, how that works. So, in my mind, there's always two ways of viewing a complex number. You can view it in rectangular coordinates, or you can view it in polar coordinates, just like you can view any point in the plane that way. So we have two different ways. So we have a plus bi. That's, you can think of this as rectangular coordinates. Rectangular AB coordinates. But for any rectangular representation for this particular number, you can also view it in polar coordinates. And we have this Euler's formula, which, you know, Zach is famously naming his channel after. Where instead you can view this number in the rectangular plane as being some radius away from the origin, right? So, right, here is our a plus bi. Oops. So a plus bi, right, sitting right here. But we can also view this number in polar coordinates. So this is a square root of a squared plus b squared, which is the radius. We can call this r. And also, there's some angle here, right? That's how we do polar coordinates. Some angle theta. So yeah, another way of writing this, because we have the Euler's formula, the e to the 2 pi I, or e to the, in general, e to the theta I, what am I saying? E to the I theta, right? So I guess I don't know what this is just the Euler formula, right? E to the I theta is cosine theta plus I sine theta. And so another way of viewing this famous formula is that it's a translation between, well, at least for radius 1. Oh, sorry. Maybe I'll just, probably shouldn't have written that at all. So this is parametrizing a circle of radius 1, and if we put an r in the front, it'll be parametrizing a circle of radius r. So this is basically your translation between polar and rectangular coordinates for complex numbers. So basically we can write any complex number as some radius away from the origin, and then e to the I theta for some angle, whatever this angle is. And of course you start it from here and we go counterclockwise, right? So, although you just kind of need to pick some 2 pi interval, you could actually go from like pi over 2, yeah. A bunch of ways you can split it up, of course. If you've seen this stuff before, then you know what I'm talking about, right? Right. So we have rectangular coordinates, we have polar coordinates. In polar coordinates, the radius, so this is like the size of the complex number. I'll put in quotes because we're not really defining what that means, but actually, yeah, I mean, you can think of it as a metric, right? So it's a real number that describes how big the complex number is, right? And the only real number with radius 0 is the origin. So I believe it is an actual metric, right? And this is just the normal Euclidean metric, right? Square root of a squared plus b squared. So yeah, this is just your normal notion of size. And then here we have, this is called the argument of the complex number. Right, and that's, I guess, just the name of it. I don't know really why they call it the argument, but maybe anybody in chat, do you know why this is called the argument? Is it because it causes people to argue? Possibly. I think that, what do they call this? Like argz sometimes I think I've seen. Like argz. Z is a complex number. You write argz. That's the angle. I don't know. Has anyone seen any other notation for this angle? I can't remember. It's quiet in chat. I guess this is a surprise stream, so I'm trying to wait for maybe to pick up a little bit more people to show up. But yeah, this is the idea. We have complex numbers. There's two different representations. You have the rectangular version here. You have the polar version here where you're dealing with a radius and an angle. Right, and so the point of this was that multiplication is essentially much easier in the polar coordinates. So when you multiply two complex numbers in polar coordinates, all you have to do is multiply the metrics together, so multiply the r's. And it follows the standard algebra rules that you would, think that e to the whatever would follow, right? So if I take two complex numbers, like r1 e to the I theta 1, and I multiply it with some r2 e to the I theta 2, then essentially what happens is what you would expect. So, the numbers are commutative in the complex numbers. So r1 times r2, you can just pull this to the front, right? This is just r1 times r2. So the metrics basically multiply. The sizes of the numbers multiply. Easier in what sense? In this sense. So multiplication is easy because we can just multiply the radii together. So we know how, I guess in my mind it works how normal multiplication works, or it works more similarly to normal multiplication in the real numbers, where like the sizes of the numbers are just multiplying, and then the only sort of like niche kind of thing that's happening here is that the angles will add. But that's just a normal algebraic property here, because we have e to some power times e to some power. And we know for real numbers it's true that e to the a times e to the b is just e to the a plus b. So you basically just have to show that still holds for complex numbers, but it does. So this is just e to the I and then theta 1 plus theta 2. Distribution is arguably easier in rectangular or more familiar. So you're saying when you take two complex numbers, yeah, I guess. So yeah, I guess you can say. Well, it works. I guess it depends on your perspective, maybe. So here, yeah, I get what you're saying. Like the multiplication is more like intuitive in a more basic sense, because you're just using like the normal distributive law, and then the only thing you need to know is that I squared is -1. Right. So I guess, yeah, I'll take that. I guess it depends on what your perspective is, to say which one is easier. Thinking from a novice point of view, yeah, I totally understand. Yeah, after you said that, I'm thinking about it now. I get what you're saying. So yeah, I guess maybe this is more from like an advanced point of view. Like this is how you would probably understand the multiplication from a more advanced point of view, but I almost feel like once you understand that, it's sort of simpler, because you understand what multiplication is doing in a more fundamental way. It's just multiplying the sizes of the radii, basically, of the numbers, and then you get this rotation of the angles, where if you take one number and then another number, the the angles just add. Here it's sort of, it's not really clear what the multiplication is doing, but you're right in the sense that actually like performing the operations is pretty simple. But I feel like it's pretty simple here too, so. But yeah, this is kind of like your fundamental two different ways you can always view a complex number in. You can always view it in these two different ways. So it's not obvious. Zach is saying it's not obvious, in my opinion, for example, why 1 plus I squared lies on the imaginary axis only. Right. From the rectangular coordinates, that's not obvious, right? 1 plus I, you would, well, it's obvious once you do out the distributive law, right? But sort of like the intuition behind it is not obvious. Whereas in this point of view, 1 plus I has an angle of 45 degrees here, and if I multiply it with itself, 45 degrees plus 45 degrees, I'm going to get a 90-degree angle. So it will be on the positive imaginary axis. So that's Zach is basically pointing out this intuition here, why this polar coordinates form gives you certain more advantages in thinking about the problem, depending on what the problem is. So yeah. What else should I say about this? So we have rectangular coordinates, polar coordinates, and I believe the name of this theorem essentially is like, maybe there's like different forms of this, but this is essentially de Moivre. I'm not sure how to pronounce this. I think that's how you spell it, though. Theorem. Somebody correct me. This is probably not the right spelling. But yeah, this theorem essentially says that the sizes of the numbers multiply when I multiply complex numbers together, and that the angles, the arguments of the numbers, this argument, this theta, the thetas add together. Okay, let me see. I thought I'd have more questions by now. So yeah, if anybody has any questions about the complex numbers or any sort of like real analysis, calculus, group theory, anything like that, linear algebra, please join the Discord. So let's put the Discord again in the chat. And yeah, so please put any problems there. You can put them in the general or the Wednesday section, and we'll tackle them, or we'll try to. Zach says, what does it mean to be a function of a complex number? Okay, that's a pretty good place to start. Yeah, so the book, the resource I put in there, I believe the name was, what was it? Function theory of one complex variable, right? So what is a function of a complex variable? Well, we already said it has like basically two components. So we can somehow think of it as like a function on these two real numbers, a and b. Okay, so essentially we have a plane of numbers as the domain, right? So we have some, a plus b, a plus bi. We're plugging that in the function, and then we're getting another pair of numbers. So we're plugging this into some f. It could be any function. We're not saying anything about the function, just that it's a function. And so we plug in a plus bi, and we get out some other complex number. So we can call the first component u of a plus b, or u of a comma b. And the vertical component we can just call y, v. I mean, they call it v. So this would be like v plus u plus vi, or u plus iv. So this is some v of ab. So what I'm saying is essentially that if you want to think of a function from the complex numbers to the complex numbers, you can essentially think of it as two functions of two variables. So each component of the codomain depends on both a and b, and there's two components of the codomain, so there's both a v and a u. So there's so it's essentially two functions of two variables. It's u of ab and you have v of ab. So u of ab, u of ab and v of ab. Okay, so two functions, each one is of two variables. And then the question becomes, well, you can add extra, constraints on these variables. Like you can demand that u and v are both, once differentiable, twice differentiable, or maybe that they're twice differentiable and the second derivative is continuous. So I believe there's a theorem that, well, we haven't really talked about what a complex derivative is yet, but you essentially want some sort of conditions on when is this thing nice enough so that it has a complex derivative. And we haven't really defined that yet, but let's just put that as a question. So what do we need for f to be quote unquote complex differentiable? Okay, so that's the sort of fundamental question here. Yeah, the only thing I don't like is that, I wonder how I can get rid of that reflection in the middle. Right, so any function from complex to complex, you can view it as two functions of two variables, of two real variables. But then the question becomes, so what do we want to say about u and v so that it has some notion of complex differentiable? And it turns out that complex differentiable is like a very restrictive condition. So we'll get something called the Cauchy-Riemann equations that relate the partial derivatives of u and v. And it says, if u and v are C2 functions, which means their second derivative is continuous, and if u and v's partial derivatives satisfy the Cauchy-Riemann equations, that's if and only if it has this notion of complex differentiable. So, yeah, without going too much into what complex differentiable means, just know that it's basically a restriction on the partial derivatives of u and v. So they have to agree in some sense, I believe. Maybe I have this wrong, but I think it's that the derivative of u with respect to the first variable, so here a, has to be equal to the derivative of v with respect to a. And then I think the other one needs to be the negative, right? So du db needs to be negative dv. Or no, I got these backwards, right? Du dA has to be dv db, and then du db has to be negative dv dA, I think. So these are called the Cauchy-Riemann equations. Did I get this right? I think I got this right. So the first variable derivative of u needs to be the second variable derivative of v, and then it's similar but negative. Okay, and then so if you have two C2 functions, u and v, that satisfy these, then that's essentially, it will be equivalent to this notion of complex differentiable. And complex differentiable, the definition is very similar to the the real case, remember we had this like limit as h goes to 0 of this stuff. So it's the same thing, except we're going to replace what we're plugging into f, right? So it'll be like limit as h goes to 0 of f of a plus h minus f of a over h. But now f is allowed to be a complex number. So saying that this limit exists at some point a is a much more restrictive statement than saying that it exists for a real function. Basically because we have these extra dimensions, and then so if you know that this limit exists in some for some point a, then you can show in that neighborhood of a that the functions u and v here, if it's complex differentiable, then they satisfy the Cauchy-Riemann equations. So that's basically the translation of this. Like essentially you assume this and you can show there's this restriction on the partial derivatives. Welcome to the chat. So just talking about complex numbers here, a little bit informal introduction. I'll get into more formal stuff on Friday, but yeah. Any questions about this? Get a little bit of water. Where should I go next? I don't want to go too far out and confuse everyone. What is this called? So this is complex analysis. If you weren't here earlier, we're essentially dealing with the real number line. We added an I to it, to the real number line. So now we have a new dimension of numbers. Everything that's multiplied by I goes along this y-axis. And I has this property that when it multiplies with another I, we get -1. And we want this number system to obey distributive property and stuff like that. So essentially, just including this I and knowing that I squared is -1 and having the distributive property, you can show that any a plus bi, if I multiply it with another number of this type, the i's basically multiply to give you -1, and you just get some other complex number. So we're dealing with a two-dimensional number system, and then essentially we're just talking about what does it mean to be complex differentiable. So we had a notion in normal calculus for a derivative of a real valued function. So this is like a generalization of that, except now the f here is not a real valued function. It's I put a plus b here, but it should be a plus h. But now that this h here is changed to a complex number, and the a here is a complex number, and we're doing the addition in the complex numbers, and we're plugging it into a complex function, so the output is also complex. So f of a plus h is complex, and I subtract f of a, that's also complex. And then I divide by h, which is also complex, so I get another complex number. So the fact having this limit exist for f is a lot stronger of a statement than like having this limit exist in any of the real directions. Like if I restricted f to just being the real part of f, and if I restricted a and h to just being the real part of a and h, then you know, that would just be saying that, you know, it had some derivative in some real direction. But yeah, so this is a stronger, much stronger notion. What makes a function differentiable if you can take the derivative? Well, I mean, this is the definition. So a function is complex differentiable at a complex number a. Let me start over. A complex function f is complex differentiable if for some, at a point a, if f of a plus h minus f of a divided by h has a limit as h goes to 0, but again, you need to be taking any possible sequence of numbers to 0 in the complex plane. So it's a little bit more restrictive than the real definition, but visually it looks the same, right? Like if you look at this definition, it's literally the exact same definition, except now the F is complex, the A is complex, and the H is complex. And you're doing, subtraction in the complex numbers, and you're doing division in the complex numbers as well. Right. So it's essentially just an extension of our notion from normal calculus, but now we're including this, this new number system that includes this extra dimension of. So there's essentially more stuff going on. We have an extra dimension of things happening. Right. So maybe we could just look at some fun. Or actually, no. Let me talk about z and z bar. That's probably a good place to go. Right. So you have this rectangle. So we talked about the rectangular way of looking at things, the polar way. There's actually another way. We can actually view any function, any complex function from complex numbers to complex numbers. We can view it as a function of these two things called z and z bar, which always confused me when I first learned this, but now I've eventually finally understood it. So let me just give you an example. Like we could send z bar to z plus z bar, something like that. So this is a function of z and z bar, and we have a translation from rectangular coordinates to these z and z bar because we just say that z is a plus bi, the normal z, the rectangular version, and then z bar is called the complex conjugate, and this is a minus bi. And these are, in some sense, these two numbers are linearly independent over the real numbers, so they span the complex numbers as a real vector space. So any complex number I can write as some linear combination of these z and z bar. And that's important because essentially it's a translation between the normal coordinates a and b here and these z and z bar coordinates. Yeah, Rex, we're going for a 4-hour stream. I got the hydration going. We're staying positive. We're thinking about math. So yeah, another way of viewing complex functions is you can view them as some function of z and z bar. And this is sort of useful because the Cauchy-Riemann equations are usually kind of annoying in some sense. And you can also show that the property of being complex differentiable at a point is the same thing as saying that the derivative of that the derivative at that point is 0 with respect to z bar. So for instance, this function, if we ask the question, is this complex differentiable at the point, let's say z equals 1 plus I, who can tell me what's the answer here? So if I look at this complex function here, z bar goes to z plus z bar. Is this complex differentiable? So the question is, does it have a limit at this point? So we'd be taking like a limit. Well, essentially you never want to use the limit definition, but by the limit definition we would be asking if this limit exists. So 1 plus I plus h minus f of 1 plus I over h. And we want to know, does this limit exist? And if it doesn't exist, how can we show it doesn't exist? 2. Yeah, that's the output of the function, but I'm asking, is it complex differentiable at this point? Yeah, so I mean, yeah, Rex is saying that's the output. That's important too. So yeah, I mean that's a good example of showing how we can plug in something here. So 1 plus I plus 1 minus I gives us 2. So in this case, if I plug in for this particular z, this is 2. But yeah, we want to check if this limit exists or not. So one way to show that a limit doesn't exist is to pick two different sequences where h goes to 0, where this number is not approaching the same number, or it has two different limits, for example. Or maybe it has no limit at all. So we're looking at this point, 1 plus I, and the value of the function is 2 there. So this is 2. And then I can start plugging in h's. So let's see, if I start traveling in one direction in h, what happens? So I have the value of 2, but maybe if I go in the direction of h where I'm adding some small like I number, like epsilon I, for example. So let's say h is I times epsilon, where epsilon is just some real number greater than 0. Then this limit looks like, so f of 1 plus I is 2, and then when I add in this small I part, the z bar makes it negative, so I actually get 2 minus I theta, or I epsilon, I mean. Yeah, for these h's. Oh, sorry. And then I need to divide by h, right? Okay, so we get 2 over I times epsilon minus 1. And since epsilon is going to 0, this is like dividing by 0, right? So this whole thing is going to infinity. All right, so now already we know the limit doesn't exist, right? Wait, is that right? I can't be right. The derivative is infinity. Seems wrong. Oh, wait. Wait, no. What did I do wrong here? Oh, 2 minus, oh, right, my bad. Oops. This is wrong. So it's f of this, so it should be 2 plus I epsilon minus 2, right. Right? Okay, so the 2's cancel. And then negative I epsilon over I epsilon, this is going to negative 1, which is equal to negative 1. Oops. Okay, so basically, when we approach this limit from this direction, where we're just approaching it from the positive or negative I direction, then we get a constant, which is negative 1, so we get a limit of negative 1. Although if we approach from the real direction, so instead of h being some I times epsilon, where epsilon is a real number, h is just some real number to begin with, some epsilon here, then things change a little bit. So then we get, so if it's a real number, then this z bar basically doesn't matter. So it just becomes 1 plus 1 plus some I epsilon, or some epsilon, right? So it's like, it's very similar to this. It's just instead of minus I epsilon, it'll just be plus epsilon. So it'll be epsilon on top, epsilon on bottom, so the limit is 1. And since the limits don't agree, then this limit doesn't exist. Because we approach the limit from one direction where h is, plus or minus some imaginary number, and approaching 0, and we get a limit of -1. And if we approach 0 from the positive or negative real axis, then we get a limit of 1 over here, epsilon over epsilon, which is 1. And so the limits don't agree because it depends on how I'm approaching this 0. So even though this function is actually it's differentiable, it has all its partial derivatives, it's actually infinitely differentiable. It's a polynomial in z and z bar, which means it's infinitely differentiable as a normal function, as a real function of two variables. But if you view it as a complex function, then this limit doesn't exist like simultaneously. It depends on which how you're approaching 0 in the complex plane could possibly change whether the function is differentiable or not. I couldn't come for here. Sorry, I'm reading the Snake King chat. So I couldn't come here for so long because I had so much school stuff. Now it's calmed down and I can finally chill here for a bit. That's good. Sounds great. I'll be here till 4 o'clock. Or no, sorry, 5 o'clock. So 4 hours total. We'll take a little bit of maybe 30-minute break in the middle, but yeah, I'll be here for the next few hours. So you can approach it from any direction. Yeah, Rex. So we should be able to approach it from any direction. If this limit exists where h is a complex number, essentially I should be able to approach the origin here along any path, even some weird path where maybe I go in like some sort of spiral or something, right? So I should be able to approach the origin. This h should go to 0 along any possible sequence as long as its limit is 0, and this ratio needs to be approaching a limit in the complex plane. If it does, then we say the limit exists and it's complex differentiable at that point. But in this case, we showed that the limit can exist because it depends on how we're approaching 0. If we approach one way, we get a limit of -1. And if we approach this other way, we get a limit of 1. But another way of thinking about this, which I prefer, is that you look at the function as a function of z and z bar, and it needs to have a derivative. It needs to have a partial derivative, quote unquote, partial derivative with respect to z bar of 0. So if df dz bar is 0, and maybe you need some condition on the differentiability of f of like the partial derivatives or something, but if you have those and the partial derivative of f with respect to z bar is 0, then that's if and only if the function is complex differentiable, if and only if this limit exists. But again, I think maybe you need some condition on f, like you have to be a little bit careful. But yeah, so here if it's a polynomial, then you can, then you're fine. You can just check, is the derivative with respect to z bar 0? In this case, we see that it's not, except for at one point. So what's the one point where this function actually is complex differentiable? But I guess it's not in any, it's not in any open neighborhood. Okay, yeah, there's a little bit of, it's all coming back to me, but there's, you need to be a little bit careful about, like the analytic stuff and complex differentiable. Yeah, I think it needs to be on an open neighborhood, this derivative needs to be 0. Or else, like in this case, the derivative of z bar actually is 0 at 0, but not in any open neighborhood of 0. So yeah, you have to be a little bit careful about that. But if you have an open neighborhood where the partial derivative of f with respect to z bar is 0, then it's what we call holomorphic in that neighborhood, or it's complex differentiable in the open neighborhood. So essentially, we never want to use this definition ever. It's the definition of complex derivative at a point, but just like in the one variable real case, you almost never want to use this by hand. You're usually checking, what's the derivative with respect to z bar? Is it 0? Is it 0 on an open set? If I think it's not complex differentiable, can I show that the limit doesn't exist? Here we showed that it didn't exist. Okay. What else can I say? Does anybody have any questions about complex functions? Definition of complex derivative? How to multiply complex numbers? That's what we're focusing on here. So. We still have no problems in the Discord. Let me check the Discord on my phone. Oh, Famished is back. So what if you add another axis to the complex plane, like a real or imaginary axis? So you're saying you want like a three-dimensional system of numbers? I don't know about this stuff, but I think somebody showed that there's no three-dimensional number system where, I forget what it is, but like there's basically no way to extend the complex numbers to 3D where you still preserves, I forget the nice stuff, like you definitely can't have commutativity for sure, but then also like I don't even think even non-commutative, I don't think it works either. Like there's no way to have like a normed three-dimensional space where the norm is respected by the multiplication, I think. So then the next best thing you can do is extend it to 4 dimensions, and then you have the quaternions. So I don't want to go too much into the quaternions, but this is a 4-dimensional number system now. But the problem with the quaternions, which means that they're not very useful for a lot of things, is that they're not commutative. And a lot of the algebraic topology stuff I do, I need a commutative ring. That's essentially like a real necessity for a lot of the calculation stuff. So you can include like a plus bi plus cj plus dk, I think they use, and then you have that I squared is j squared is k squared is -1. So now you have a 4-dimensional system, so this works, but then again, like we said, it's not commutative. I think you also have ijk is also -1. And I believe ij is equal to like -ji, so it's not commutative. It's like almost commutative. You could think of it as like, it's like skew commutative, right? It's like most of the numbers commute except the variables are like skew symmetric. So very, very close to being commutative, but this negative sign messes everything up. But yeah, this is your next largest number system where now you still have a norm on this space, and the norm is respected by when you multiply the two numbers together, but yeah, it's still a little weird though, because like -1 here has norm 1, and I'm multiplying 3 things of norm 1. So the norm is being respected here. I have 3 things of norm 1, I multiply them, I get something else of norm 1. But this skew symmetry stuff is not good for a lot of like things where the complex numbers, it is good. Okay. Let me see. So yeah, we basically don't use these though. At least I don't. I've never seen them used for anything, at least in like higher math, except for, I guess maybe that's not true. They're used for like some computer graphics stuff, I think. Maybe, but I'm not even sure why. I mean, everything you can do in this number system, you could just view it as like a 4-dimensional number system. You don't really need to include these I, j, and k. They're kind of just for and maybe they make like hand calculations a little bit easier or something. But yeah, I mean, you could do everything as just like a comma b comma c comma d. You don't really need to write the I, J, K. All right, well, if there's no questions right now, I'll take a little bit of a break at 2, and you guys can join the Discord if you haven't already, and put some questions in the Discord. So let me put the Discord here. Yeah, so we'll be back in, let's say 10 minutes. For now, I'll take another break in a little bit after, maybe in another hour or so, and yeah, we'll just do more math and we'll just keep going all day. So thanks guys for showing up, and I hope we can get some good questions in the Discord when we get back. Sure. Let me see. Okay, yeah, I'll play some music. So 10-minute break.
The Mediterranean diet is the world's healthiest diet, and Factor makes it easy to eat that way every day.
All right, yeah, so please join the Discord and put any questions you want us to go over in the next few hours in the Discord, and we'll go over those. Wait, Zach what? Zach's just borked? What, his stream crashed? Or what? Alright, let me get the Discord up and we'll look at some problems if we have any in here. Okay, looks like we got something. Okay, so we have a problem from Rex, problem from that snake JNDR. Oh, is it just mobile? He's just having problems on mobile, or it's on everything? Oh, why does it have me starting sooner? Okay. Alright, let's start back up again. Get rid of the music. Okay. Alright, so thanks for joining. This is the mathpond channel, mathpond stream. We do math exercises on Wednesdays, so that's what I plan on doing. We got a couple in the Discord here, so if you're just joining now, you can put any problems you maybe want us to talk about. They can be complex analysis or otherwise. Linear algebra, calculus, anything like that is totally acceptable. And yeah, so let's take a look at the Discord questions. So first Rex posted a question, so I'll just go in order. So Rex asks, what is the stereographic projection of this complex number? So let's just draw a little picture first to explain what this stereographic projection is. So we have this XY plane here. We can view with a ball sort of sitting on the origin. So use your imagination that this is sitting here. And we take the North Pole here and we project, basically every number on the complex plane has an associated number on where it's basically hitting this sphere at a tangent point. So the question is, we have 1/2 plus square root of 3 over 2i. Or, sorry, square root of 3 over, yeah, that's what I said. Square root of 3 over 2, wait, was that correct? Square root of 3 over 2i, yeah. And we want to know, the question asks, or Rex asks, is this in the upper, lower hemisphere, or the equator? So this sphere here has an equator, right, that goes all the way around. It's like a really bad picture here. But yeah, use your imagination a little bit maybe. Okay, so yeah, first of all, let's just specify this is the positive. How do we want to do this? I guess this is the, yeah, let's make this the imaginary axis. So this is the y-axis, this is the x-axis. And so where would this number be? Well, it's in the positive real side, so we're going out like some amount this way. And then it's also in the, this way. And then it's also in the imaginary direction, so somewhere here. Okay, yeah, so basically, if we look at all the points on the equator, it's going to split the plane into two halves, right? So I think that's the way we want to view the problem. So yeah, if we look at the equator points, they sweep out like a giant circle, I think, in the plane of some radius, but I'm not sure how big this is. Probably radius 1, I'm assuming. Is that right? I haven't really thought about this. This is a good question. So the points in the upper half of the sphere and the lower half of the sphere, they're separated by this equator, right? If we project the equator onto the plane, do we also get another circle? And if so, then the upper half plane would be basically projected onto the outside of the circle, I think. And then the lower half plane would be projected to the inside. So you get this like splitting where the equator is this great circle that goes around, and then it splits the plane into these all these points. See, all the points in the upper half of the sphere, they get mapped to like really far away points, right? But all the points in the lower half, they get mapped to points that are closer to the origin. So unless I'm thinking of this wrong, this number is right on the equator, right? Or it's right on the circle of radius 1, because 1/2 squared is 1/4, plus this squared is 3/4, which is 1, right? So it's a complex number of radius 1, or of magnitude 1. Or I think they have like a bunch of other weird words. They love making up words in complex analysis for things that we already have words for, like argument for the angle, and is it modulus? Yeah, modulus for the radius or the size. Okay, correct. Yeah. So yeah, I believe this picture is correct then. The equator, if you project the equator to the plane, you're going to get this circle of radius 1, and the upper half plane is going to get mapped to all the large numbers out here, and the lower half plane is going, or the lower half of the sphere, of the surface of the sphere, will be mapped to the inside. And then every point of that's exactly on the equator will be mapped to the points that have exactly 1 modulus. One little gold star for Maddie boy. Yeah. Yep. Gold stars. How do you do a star? Well, I'm really bad at drawing. Okay, yeah, that doesn't count. No one saw that. Okay, yeah, so, I mean, that was a good question, because, yeah, it goes over this can't talk today. Stereographic projection, but it also, we talked about modulus of a number, the size of the number here matters, right? So breaking the plane into numbers that are bigger than size 1, smaller than size 1, and all the numbers that are exactly size 1. That was a beautiful star, thank you. Okay, so let's go to another problem. So we have a problem from that snake. The lengths of the edges of a rectangular prism originating from the same vertex are in a ratio of 1 to square root of 2 to 2. Lengths of the edges of a rectangular prism. Okay. the area of the face with the shortest face, the area of the face with the shortest face diagonal is S, which is equal to 2 times square root of 2. What is the volume of the cuboid, or the entire rectangular prism? Okay. Sounds reasonable enough. So yeah, I'll probably just draw a picture here to start to get bearings on what's going on. Let me say Jake. JNDR on Discord. So this is their problem. Lengths of so we have rectangular prism. Like this. What do I do here? Did I do that right? Yeah. Okay. That's good enough, right? It's close. Okay, so coming out of one vertex, we have 3 different side lengths, and they're in ratio of 1 to square root of 2. So we'll say this one's square root of 2 going up, and then the width here. So call this length, height. So length is 1, the height is square root of 2, and the width is this one, which is 2. Let's do it like that. So this is L, 1 is L, square root of 2 here, this is H, and this is W. Okay, and then the question asks, what is the volume, the area of the face with the shortest face diagonal is S equals 2 times square root of 2 centimeters squared. So the smallest diagonal, what would that one be? Smallest face diagonal. Oh, okay, so that would probably be these 2 sides. So on the side here we have a diagonal here, which is 2 times square root of 2. And then the length is 1 and the height is square root of 2. So does this make sense? 1 squared plus square root of 2 squared is 3. That doesn't make sense. Is this, what am I doing wrong here? 2 square root of 2? Is that possible? The area of the face with the shortest face diagonal. Yeah, I don't know if that's possible. Is that possible? Or am I just looking at the wrong one? No, it's got to be the right one. Oh, am I looking at the wrong diagonal? No, that's there's only 2. They're the same length. 1 squared plus, yeah, it should be square root of 3 over here, right? What am I seeing? Yeah, I'm not so sure about your problem, Jake. Something seems off about this. I don't see how this could be right, because 1 squared plus square root of 2 squared is square root of 3 squared. Right, so this diagonal should be square root of 3, so I don't know what it means that we're assuming it's 2 square root of 2. Unless we can correct this, I'm not sure if I understand. Oh, sorry, I need to multiply. Okay, I see. I just have the ratio. I get it. Okay. Oh, okay. Right. Okay, so this is supposed to be, okay, so 2, so cube root of 3 over 2 square root of 2. So yeah, we basically, this is some constant times 1, this is some constant times square root of 2, and this is some constant times 2. Now they're in a ratio. Okay. Okay, sorry, this doesn't make sense, right? Okay, right. And now we get alpha squared plus 2 alpha squared is 2 square root of 2. And now we have to solve, so this is 3 alpha squared is 2 square root of 2. Alpha squared is 2/3 square root of 2. So yeah, alpha should be the square root of that, which is something. Yeah, I'll just say it's the square root of 2/3 square root of 2. Yeah, positive square root. So yeah, then what would the volume be? Is that the question? Yeah, so what is the volume? No, I think you're good. So what is the volume now? Should be length times height times width, but this, I forgot the epsilon here. So these are all multiplied by or sorry, some alpha, I mean. And alpha is this square root thing, right? So if we multiply them all together, yeah, let's, I'm not using a calculator here, so maybe it's a little bit easier, or maybe I'm going a little bit too quickly, but in the end, if we multiply these all together, I should get alpha cubed 2 square root of 2. So 2 square root of 2 alpha cubed, where alpha is this square root. So should be 2 square root of 2 times 2/3 square root of 2 times the square root of that. Which is 8/3 2, 8/3. All right, maybe I did something wrong. Yeah. What did I do? Should be 8 centimeters cubed, apparently. Huh. Is this 3? Then that would make sense. But I don't think it is. What did I do wrong? 2 square root of 2 alpha cubed. Huh. Squared plus this squared. Oh, it needs to equal this squared. Oops. Okay, yeah, I had the wrong thing here. Okay, I forgot to square the right hand side. So it should be 2 squared to 2 squared, so 4 times 2, which is 8, right? So alpha here, so 3 alpha squared is 8, so alpha is square root of 8/3. Then if I multiply them, I get 2 square root of 2 alpha cubed, and we get 2 square root of 2 times 8/3 times square root of 8/3. And that is 2 square root of 2, so yeah, a lot of stuff is what's going on here. So it's 2 square root of 2 times 2 square root of 2 times 8 all over 3 times square root of 1/3, I think. I feel like I'm doing this too fast. 2 is 8 times 8. Yeah, something's wrong. Well, I'm not getting 8. Let's see. Alpha squared plus 2 alpha squared. Huh. 3, 8. Yeah, I don't think I'm getting 8 here. Unless, so this is like 64 over 3 times square root of 1/3. Or, 64 over 3 times square root of 3 over 3. Which is 64 square root of 3 over 9. But you're saying it's 8, so that's not what I'm getting. Does anybody have any ideas about this one? So yeah, Snake King, I'm not getting 8, but I think this is like close to 8. It's a little bit more, I think. So yeah, what did either this is right or it's not right, but let me see. I don't have the exact way to get to it. Let me try and find it. Yeah, I don't see what we did wrong here. So we have the side lengths. We have one is alpha, one is square root of 2 alpha, and one is 2 times alpha. They are in the correct ratio, and then the smallest diagonal should be this one. And then alpha squared plus 2 alpha squared needs to be equal to the diagonal squared, and the diagonal, they said by assumption, was 2 square root of 2. So that squared is 8, so that's how we get this equation. So it's a squared plus b squared equals c squared. Solve for alpha, we get alpha as the square root of 8 over 3, and then I think this is right. Or at least, yeah, what I did here. Yeah, 2 root 2 8/3 times the square root of 8/3. I only have the answer. Let's see. Yeah, I mean, it's totally possible I did something wrong here and I just don't see it. So maybe somebody in the chat can see it, but otherwise, I mean, yeah, I don't see anything I did wrong. Maybe I'm looking at the wrong diagonal. I don't think so, though. Alpha squared plus 2 alpha squared is 8. 3 alpha squared is 8. Huh. 2 square root of 2 alpha cubed. 8/3 square root 8/3. Yeah, I don't see it. All right, well, if no one in the chat can see anything wrong with this, then I guess I'll just have to move on. So we got an answer. It's not 8, but yeah, I don't see how to get 8. So unless I'm just taking the wrong diagonal, which is possible, I guess. But this, I feel like, yeah, this has to be the smallest one, right? Oh, wait, no. Yeah, if alpha is greater than 1. No, yeah, no matter what alpha is, this should be the... Did it say the smallest one or the largest one? Face with the shortest face. The area of the face with the shortest face. Face diagonal. Oh, the area of the face. Okay, yeah, I misread the problem. Okay. So the area of this face is 2 square root of 2. Okay, my bad. So it's really we want alpha times square root of 2 alpha to be equal to 2 times square root of 2. Wait, why did it say with the face with the shortest face diagonal? Okay, I just misread it. So this is 2 square root of 2. So alpha needs to be square root of 2. Okay, right. Okay, now this is wrong. So yeah, so this doesn't matter anymore. So if alpha is square root of 2, then the volume is still 2 square root of 2 alpha cubed, but now alpha cubed is 2 square root of 2, so it's 2 square root of 2 times 2 square root of 2, which is 8. Yeah, okay, now we're good. 8 centimeters cubed. Okay, all right, so that was a little tricky, but mainly I just tricked myself, which happens. DAB equals x square root of 3. What are you writing here? I'm confused. But yeah, I think we're good here. So the volume is the product of the 3. So it's 2 square root of 2 alpha cubed. If alpha, we just proved it was square root of 2. We take the product, we get alpha cubed here. This is 2 square root of 2 times 2 square root of 2, which is 8. Since 2 square root of 2 is the square root of 8. Okay. Any more on this stuff right here? So we had a cube. It had 3 different side lengths, but we wanted them to be in a certain ratio. So we basically took those numbers that were the ratio and we took a constant and multiplied by all of them. We called that constant alpha. Then we wanted to say that the volume, we wanted to figure out what the volume was. So first we need to figure out what alpha was, but they gave us the area of one of the faces. So we knew that alpha times square root of 2 alpha was 8, or was the square root of 8, was 2 square root of 2. And that meant that alpha was the square root of 2. Because we have that alpha squared, square root of 2 alpha squared was 2 square root of 2. So alpha squared is 2, and alpha is square root of 2. I think I get it now. Okay, good. Yeah, I mean, the only problem with these is like if you do what I just did, which was misread the problem, then you can, you'll be calculating something maybe correctly, but you'll be solving the wrong problem because you just misread it. Once you figure out what you're supposed to do, then the math is pretty easy here. You just need to multiply these 3 numbers together and figure out what they are. Okay, let's see what else we have on the agenda here in the Discord. So, got a couple integrals from Rex. I don't know if I want to jump right into the complex integrals immediately. Okay, what is the mean value of this function on a set of points? That one's interesting. Find the radius of convergence. Okay, yeah, we haven't really, that's a little bit too advanced, maybe. Residues, maybe a little bit more advanced. Yeah, okay, so let's look at the mean value of this function. That's a good one. Not that the other ones aren't good, but just gonna take a little bit more explaining than this one. And this one's sort of probability related because the way it's worded, it's essentially a probability problem. Because we're asking for the mean value. So if we had a random variable that was, taking values with some distribution on this circle, right? So the question from Rex is, what is the mean value of this function? So what is the mean value of u? U of xy, which is x squared minus y squared plus 1. And we want to know what's the mean value on a circle of radius 1 centered at 1, 1. Right, so the picture is you got 1, 1 here, circle of radius 1 looks like that. It should be, connecting here perfectly. Radius 1. Right, so we have a function, and we can plug in any of these points on this circle. Each point is some xy. We can plug it into this function. We get some value. And if I'm talking about the mean value of this function, what do I need to use to find the average value of a function on some domain? So this is like a calculus problem. It's really a probability problem, but we use calculus for probability, right? Yeah, Snake King, if you want to find me the one from a while ago, the probability ones from a while back, yeah, you can repost some of those. Yeah, we definitely didn't tackle all of them. I think we got through maybe half of them. Okay, so yeah, how do we solve a mean value problem? So this is like a calculus idea, at least. It's going to involve an integral, right? So we're going to take an integral and then we're going to divide by, in some notion, the size of the domain that we're integrating over. Oh, wait, is this on the boundary of the circle or the inside? Let me see. Over a circle. Yeah, Rex, is this over the boundary of the circle? Or I guess if it says over a circle of radius 1, I guess they want the average value for the inside of the entire interior, right? Is that what we're asking? Okay, so that would mean that we're going to be taking a double integral of u. I'll write dA, but really it's like dx dy. And this will be a double integral over this. I'll just write disk d. A little disk of centered at 1, 1 of radius 1. I'll just write it like that. Okay, so it should be some sort of double integral. Yeah, so this, we haven't really gotten to this in multivariable calculus, but for a double integral, you can, let's see, maybe in polar coordinates it's easier. Yeah, probably want to switch to polar coordinates and then take a double integral in polar coordinates. So when you switch to polar coordinates, though, there's something funny that happens. So this little infinitesimal term picks up an extra factor, and that factor comes from the volume form that basically comes from this when you change coordinates to polar coordinates. So you're going to pick up like, I think it's like an r dr d theta. So you pick up like an extra r down here. And that's because dA for the polar coordinates is like r dr d theta. So yeah, this is a little bit of a common thing that people forget. When you switch to polar coordinates, the infinitesimal part picks up this little r factor. So yeah, so let's switch to polar coordinates here. We have x squared minus y squared. So yeah, we want this double integral, but we want to write this out as a double integral in polar coordinates. So this is going to be, let's see. So x, let's just figure out what x is. This is r cosine theta. Polar coordinates, y is r sine theta. So x squared minus y squared is r squared cosine squared theta minus r squared sine squared theta plus 1. And we want the double integral of this from a radius of from 0 to 1 and from theta from 0 to 2 pi. So it's essentially going to be, yeah, double integral. Not sure which one needs to go first. Yeah, let's just do r first. So 0 to 1, 0 to 2 pi. For the angle, because, oh wait, sorry, that's not right. Oh wait, do we want polar coordinates? I guess maybe we don't want polar coordinates. I guess not the standard polar coordinates. Yeah, that wouldn't work. How do we, okay, so how do we take this integral then? I guess we could just do it rectangularly. Oh, and we need the mean value also. I'm totally doing this wrong. So yeah, then we just need to divide by the area of the thing that we're integrating over, which is a circle of radius 1. So it's going to have area pi. So yeah, basically we just take the integral of this function, we divide by pi. So it should be double integral over this disk, I'll write as d of this function, dA, and then divide by pi. Okay, so I think this is what we want to calculate. Notice that u of xy is a harmonic function because its Laplacian is 0. Okay. Oh, okay. Sure. Right. Okay. Right. I haven't done this stuff in a while. Let's see. So du dx d no. Yeah, d squared u dx squared plus du dy squared d squared dy squared is 2 minus 2. Wait, is the Laplacian 0? Second derivatives, sum of the second derivatives, right? Or is it the sum of the first derivatives? No. U with respect to x. So 2x, then 2. Oh, 2 and minus 2, right? Okay. Okay, so Laplacian is 0. Right, and then Rex is pointing out that when the Laplacian is 0, this is a special type of function which we call harmonic. They're very closely related to the real and imaginary parts of a holomorphic function, which we were just talking about before, which is this notion of complex differentiable. And right, so this, any function that's Laplacian is 0, which is the sum of the second derivatives. So the second derivatives with respect to x, and then the second derivative with respect to y, you add them together. If the Laplacian is 0 for the function, that means that the function is harmonic and it has this mean value property. So the average value of the function on any circle around a certain point is actually just equal to the value of the function at that point. So they're sort of like you want to think of them as well-regulated functions in the sense that their value at any point, you can calculate it. It's sort of like close to the points around it, like in the sense that if I want to know the value at this point of the function, I can look at the value of the function at some neighboring set of points, and if I take the average of the value on all these points, then that's equal to the value of the function in the middle. So it's some sort of regularity condition, and these functions that have Laplacian equal to 0, the harmonic functions, they have this mean value property. So I'm thinking that if the value of the function, the average value of the function on the boundary of the circle is just equal to the value of the function in the middle, then, and we're taking a double integral here, so it should just be, yeah, the radius times the average value, which is equal to the value of the point at the center, which is the value at 1, 1, which is 1 minus 1 plus 1, which is at 1, 1, this is equal to 1 minus 1 plus 1, which is equal to 1. So the value of the function at that point is 1. So the average value of the points on any circle around that point, the average value will be 1 also. Oh, excuse me. So yeah, basically the whole average for all of the points so if I go out some radius r, in this case it's 1, but r is going from 0 here to 1, then the average value for all the points on any of these circles of radius r is just equal to the value in the middle, which is 1. So if I take a double integral, I think it should just be, average value should be 1 for everything. The area is pi, but I have pi things. So I think it should just be 1. Because I think the integral will give you pi, and then there's an area of pi, so it should be like pi divided by pi. So it should be 1. I think that's my... I think it's just 1. Let me think. Let's see. What do people in chat think? Did I do this right? Oh, it is 1. Okay, cool. So Rex said, yeah, by mean value property of harmonic functions, the mean value over any circle is simply the value of the function at its center. Okay, right. And you can take these double integrals too because, yeah, okay, I see. Right. So does that work for any double integral? So any double integral around a point, if it's a circle, the average value is always just equal to the value in the middle, even for the double integral. Okay. Yeah, I guess so I haven't gotten too much into harmonic functions, but there's probably some generalizations. But the one that I know is the mean value property for harmonic functions, which is just you're taking the integral, the average value on the boundary of a circle of radius r, and the average value of the function should be equal to the value in the middle. But then, of course, you can sort of extend this because you can use that to then prove that like the average over some area is also, as long as it's maybe circular, I guess. So any circular area around the point, the average value will also be the value at the middle for the same reason, basically. I did not take integrals yet, so I don't know. I trust y'all. Yeah, well here, so sometimes you don't need to calculate the integral, right? Like if you have a mean value property or some sort of regularity property, like maybe the function is an even function, right? In one variable calculus, or even more nice, an odd function like sine or something, right? So sine, we know we have a regularity condition on sine, which is that it's an odd function. So if I take any integral from negative, anything, epsilon to positive epsilon, then I know that the integral is always 0 because all the negative here cancels out with all the positive. So sometimes for certain functions, the integral, we have like shortcuts for it, right? So one in particular nice is these harmonic functions in 2 variables. You can have harmonic functions in multiple variables, and there's a generalization of this, but particularly when we're talking about just 2 variables, these are even more specialized because you can show that these are actually the real part of some holomorphic function. So these are very important for complex analysis, for this notion of a complex derivative. Do you want to teach how to do addition, product, and quotient? What are you talking about, for complex or for what? No problem, Rex. Yeah, what do you mean by, are we talking addition, product, and quotient? Oh, okay, so like how to take the division of 2 complex numbers? Is that what we're saying? Yeah, we can go over it. Yeah, let's go over some basic stuff. Let's start. Maybe I'm getting a little too advanced here. Harmonic stuff usually you learn like towards the end, so. Let's just show some basics on, or we showed how to multiply them in rectangular, or in polar coordinates, but now let's just show the normal operations that we do with these complex numbers. So we can add them together, right? We have two numbers, a plus b, I, and let's say x plus I, y. And I want to add them together. Of course, we want this operation to be closed, right? So hopefully we included all the numbers that we need, such that if I add these two together, I get something of this form. And so here, I mean, if you have the distributive property and the associativity property of addition, then you can sort of pretend like these are just normal real numbers, even though they're not. So we can rearrange the a and the x to make this a plus x. This is just using the, basically we're assuming that the addition is commutative also for the I stuff. So we're allowed to move this x, for instance, to the left-hand side of the bi, and we're allowed to use the associativity to group things differently. So a plus x plus I times b plus y is what we get as the result. That's how we add two complex numbers. If we want to multiply them, then it's a little bit harder. And a little bit harder, but all we have to do is remember that we have this famous equation, or important identity here, that if we squared I squared, we get -1. But other than that, we can just pretend that we have normal numbers here. I is just some weird number that we basically can't simplify, but we do know that if we multiply it with another I, that we get -I. So when I multiply these together, I can use the distributive property and pretend like they're normal numbers. So I get an a times x. I can kind of FOIL this out, right? So a times x plus bi times x plus a times iy, and then plus bi times iy. So I get I squared by. Right, and now we know that I squared is -1, so now I can simplify this all as ax minus by, so that's the real component, plus I times bx plus ay. Okay, so this is what I was talking about before, about when we multiply in the rectangular coordinates, it's not so obvious what's happening with the angles and the sizes of the numbers here, right? So we do get a well-defined multiplication here, and it obeys, it comes from this standard distributive property and foiling and rearranging things and factoring out an I, and I'm using 3 different properties here, so it is maybe useful to a new student to go through these properties for real numbers and understand why they work for real numbers before jumping straight into the complex numbers. But yeah, we are using distributive property here. We're probably using commutativity of addition. We're using the fact that I squared is -1. We're using probably distributive property here again to pull the I out. So a lot of properties here going on, but luckily a lot of them are the same as for the real case. So the properties there's a lot of them, but they're not hard to remember. It's just, commutativity of addition, commutativity of multiplication, distributive property, associativity, stuff like that. Let me see the hydration vase. I have a small, it's not quite a vase. I have a wimpy little water, but I will hydrate. Okay. So that is how we multiply numbers. Yeah, I'm sorry. So we add numbers this way. It's a little bit simpler. We multiply numbers this way. It's slightly more complex. No pun intended. Also, has anyone ever seen this? You can view complex numbers as matrices, and then you can multiply them this way. So we can actually view every complex number as some like a... Is it this way, I think? And then if you take another matrix and of this type and multiply it, you get another matrix of this type. So you could think of complex numbers as being like two-dimensional, a two-dimensional set of numbers over the real numbers, and multiplication is just a linear transformation where you're multiplying by a matrix of this type. Now teach us how to find the argument of the number. Oh, well, let's talk about division first. At least in rectangular coordinates. Let's do the division. So let's look at the same type of formula here, but instead of multiplying, we'll be dividing this number by this number, but as complex numbers. And how to find the absolute value of it. Yeah. Let's do division first. And also maybe we could even look at the polar form. Because again, multiplication, we already did the polar form, but let's just compare this to what we get from the polar stuff. So this means we have two numbers in polar coordinates, we multiply them like this. Then I get another number, which is R1, R2, e to the I, and then the angles add, so theta 1 plus theta 2. Okay, so multiplication in polar form, in some sense, the formula is, Zach got upset when I used the word simpler, and maybe he's correct, but it's at least maybe more logical in my mind, because here when you're multiplying two numbers, it's just saying this formula is saying that the size of the numbers multiplies and the argument of the numbers adds together. So the angles add. Okay, and here you don't really see any of that. It's technically the same formula, just in different coordinate system. But here you're not really seeing that the sizes of the numbers multiply and that the angles add. So this formula, in some sense, maybe it's not simpler, but it's like more illustrative of what's going on when you're multiplying by a complex number. Right, so let's go into division now. And so division is going to have a similar formula for in polar form. So the sizes of the numbers instead is going to divide, and the angles will subtract. But in rectangular coordinates, again, it's going to be messy. So it's even more messy than the multiplication one. It's about to, you can tell this is almost, marker's almost on its last days. Oh no, I just need to wash it, but okay, let me just write division here before I forget this. And what does the chat say? I always used to do that without Euler's formula. I feel like with Euler's formula, it's sort of easier. Yeah, oh wait, you think it's easier with Euler's formula? I feel like it's easier if you just remember like e to the I theta 1 times e to the I theta 2. You just remember the formula like e to the a times e to the b. This is e to the a plus b, right? So here, if you assume that this formula still holds for complex numbers, then here you can just add the angles. So it's I theta 1 plus I theta 2. Of course, you can rewrite this as distributive property. So for me, it makes more sense to look at everything just as e to some power and assume that we have this addition of the exponents rule that still holds for complex numbers. If I know that, then then this formula is just trivial. It's just a result of the exponential powers adding. Yeah, e is so easy, yeah. So yeah, how does division work? So let's just start with polar form because the polar form is easy. Again, so in polar coordinates, let's say z1 is r1 e to the I theta 1, And we have another complex number, R2, e to the I theta 2. And we want to divide them. So Z1 divided by Z2 is R1 over R2, e to the I theta 1 over e to the I theta 2. So here again, if you assume that the complex number division and division of numbers and division of e to the power of something works the same way as real numbers, then this would just be R1 over R2. So the size of the numbers divides each other. And then the angles now subtract. So this is e to the I theta 1 minus theta 2. Okay, so division for in the polar form, again, is easy. I pretty much, like, if I'm multiplying or dividing, I would prefer to be doing it in polar form because of this. The ease of calculating this way. Otherwise, division in the rectangular coordinates can be a little bit messy. So I used to do z times cosine x plus I sine x to the fourth, or some power won't let me take a power of I. Oh yeah. When you're taking the powers of these numbers, especially, remember what we had for multiplication here. If you're taking the powers of a number, you especially want polar form, right? Because if you take a power of like this number, you're just going to get R1 to some power, and then the angles, instead of multiplying, will just add the same angle some number of times. So really the angle will just multiply when you take a power of a number. So like Z1 to the fourth power, for instance, this would be like R1 to the fourth power and then e to the 4I theta 1. So then the angles get multiplied for powers. Okay, but how does it work in rectangular form? That's the slightly trickier case. Okay, so I think that's how I used to do it. I can't really remember anymore, to be honest. Hopefully you're doing stuff in polar coordinates if you're not forced to do it the other way. This is really the way you want to think of multiplication and division, unless, of course, the question specifically asks you not to do it that way, but or maybe it's just hard to convert the number into polar form for some reason, at least, on paper or something. Okay, so how do we do this division? Maybe I'll just do it over here. So this is the polar way. But how do we do it with rectangular? So here now Z1 will be some a plus bi. Let's say Z2 is some x plus iy. And now we want to know what's Z1 divided by Z2. Well, this is a plus bi divided by x plus iy. Now, what we have to do now to simplify this is like a... well, the problem is we know how to divide things by real numbers, but dividing by complex numbers, at least initially, we're trying to define it. So it's not really obvious how we do this division unless we can sort of relate it to properties that we know hold for real numbers. So essentially I want to end up dividing by a real number, so I need to multiply on the bottom here by the complex conjugate of x plus ay. If I multiply the bottom by the top and bottom by x minus iy, so this is the thing we want to know. I can multiply it by x minus iy on the top and bottom. And what that will do is when you multiply a number by its complex conjugate, you get the size of the number. So x plus iy times x minus iy gives you x squared plus y squared. So on the bottom here we'll have, well, on the top we have a plus bi times x minus iy. And on the top, we have the modulus of the number, which is x squared plus y squared, the size of the number. Or it's just the Euclidean norm, if you want to think of it like that. It's just the normal size of the number if you view it as a point in the two-dimensional plane. Okay, so it's x plus bi times x minus iy divided by x squared plus y squared, and then we can just FOIL out the top. So this whole thing is like, and I'll just do all the simplification in my head. So it's a times x, not a times b, a times x. There should be a bxi and so plus I times bx plus bx minus ay, and then here it's ax plus by. So ax plus by plus I times bx minus ay all divided by x squared plus y squared, yeah. Okay, yeah, there we're good. Any questions about that? So yeah, when we divide two numbers in polar coordinates, very easy. You just divide the sizes of the numbers, and then the angle, you subtract the second one from the first one. So in other words, you can say that the moduli of the numbers divide and the arguments of the numbers subtract from each other. So that's the way to do it in the polar coordinate form. In the rectangular way, it's a little bit more confusing. You have to do this kind of like multiply by the complex conjugate on the top and bottom of this denominator, so then the denominator can be a real number, and then now both the real and imaginary component are both real. So this is like a standard form for the number. So this is the division of the two numbers, but it's a little bit messy. But that's just because this rectangular way is like not the natural way that you would divide two complex numbers. This is the more natural way, in my opinion. But natural is very not well defined here. I guess it depends on the application. So yeah, rectangular could be good for some problems, like for some integral type problems, but polar coordinates are particularly good for for multiplying and dividing. Polar is the way to go. Yes, that is correct. Okay, it's 3:09 right now. Let me take like a 20-minute break. So like 3:30, we'll start back up and we'll go to 5. So we'll go for another hour and a half after this break. Quick 20-minute break. So we did a 10-minute break before. We'll do a 20-minute break now. And then we'll finish up after. We got a band evader. Oh no. I would prefer the polar one. School taught me the unnatural one. Yeah, that's unfortunate. Yeah, the school loves to start with all the rectangular stuff, but I do feel like the polar stuff is a little bit more of a natural way of viewing this stuff. Okay, take a quick break here. Let me turn the camera off. Okay. All right, so 20-minute break. 20-minute break starting now. Put this stuff back up. I'll get some music going just for the ambiance. Okay, and then we'll come back. We'll look at some more problems. If you have any problems, please put them in the Discord here. Discord link is in the chat. Go to the Wednesday section especially, or you could put it in the general, but I would prefer it in the Wednesday section if you put the problem there. And then we shall go over it in 20 minutes. Let me make sure my laptop's all charged up. That's the other problem. Man, these new markers are good. I think they're too good for this eraser too. Too good for their own good. Yeah, this eraser is starting to end. Alright, maybe I'll switch to blue now. Okay guys, we'll start back up in a minute or so. I need a little bit more battery charge actually, so I can make it an hour and a half. Okay, got blue marker here. Switch to some blue. Oh, excuse me. Alright, we'll start back up in 1 minute. And yeah, in this next minute, if you are here and you want to rejoin the exercises session, the Discord is in the chat. You can join the Discord server, go to the Wednesdays section, and include your problem. We're going over some complex stuff right now, but we could switch it up in a half hour or so if we want. Yeah. You don't like chemistry and biology? So when I was in school, I liked, pretty much every subject, but yeah, I guess biology I wasn't too much into. But yeah, I get what you mean. You wish it was just all math and computer science. I like chemistry, I don't really mind biology, but I absolutely hate geography. Yeah, geography is kinda lame. I mean, it's good to know where stuff is, don't get me wrong, but I mean, if a computer can store it, then I don't feel like I need to memorize it myself, you know? That's my perspective. Okay, let's start back up now. Let's see. Okay, hope everyone's having a good day. Again, if you're just joining us, you can find the Discord in the chat with the link. So yeah, please put any questions you have on Discord in the proper section. Oh, I forgot, we're going over this problem. Yeah, so we have some problems in there now. Let's see. Rex has many. Okay, yeah, so I was looking at this logarithm one, complex logarithm. I've seen complex logarithms, sometimes they write it as like capital L, but of course we need to be careful with the logarithm for complex numbers. In general, it's multi-valued. So the problem is that when we look at something like e to the I theta, where theta is ranging over all real numbers, this is not a one-to-one function, right? So this is hitting like every possible point here multiple times, right? Every 2 pi I go around, right? So if I just keep going around over and over, it's going to be multi-valued, right? So if I try to invert the exponential function and create, some inverse, it works for real numbers because, in the real plane, it's one-to-one and onto. It's monotonic, everything's nice for real numbers, but for complex numbers, it's not, for the exact reason I just showed you. So yeah, this logarithm function, it's not technically a function unless you restrict this angle. So essentially, this angle needs to be, what is the standard one? I think it's like theta is between, negative pi over 2, pi over 2? So basically like from here all the way up to, no, that would just be to here. So yeah, what is the restriction? 3 pi over 2? I forget what's the standard restriction for complex logarithms. I'm actually not sure. I'm not sure what this is, how this is defined. But basically the problem here is the not one-to-one part about going around this circle. So we need to restrict the angle to some angle range where it is one-to-one. I like chemistry. I don't really mind biology, but I absolutely okay, yeah. I'm not sure either. Yeah. So I have to think about it for a second. I mean, essentially they're all sort of equivalent, right? That's probably why it's hard for me to remember. So these are called like branch cuts, right? For a multi-valued function, you can sort of restrict the domain, and you can create a branch cut in it. And this is just like one branch reviewing. Yeah, nobody Rex. Nobody cares. Let's make our own laws. That works too. For some reason, I feel like I remember it's this, but I could be wrong. Let's reinvent it. Yeah, that's Rex's idea. So, yeah, basically, and they usually capitalize the L here. I don't know. I guess that's supposed to make you think that it's a complex number here. It's not your normal, your normal lower. This ain't no lowercase log. This is uppercase log, right? So yeah, it's some complex number, but we want it to be an inverse to e to some power, right? It's just the problem is that yeah, again, this function is not one-to-one. So yeah, as long as we restrict z to being some complex number where we restrict the argument to be in this range, then we can define the logarithm and have it make sense and have it be well defined. So essentially, yeah, let me just write it here. Need to restrict theta in, theta equals the argument of z. This angle we were talking about. The argument of the complex number is the angle that the number makes in the plane with this, how far you need to go around this, right? So for here, this would be the argument of this number. Okay, so math mutiny in the pond. Yeah, of course. This is just standard stuff, though. Standard mutiny. Wait, what's the argument again? What do you mean the argument? So the problem is that the exponential function is not one-to-one. If we let the angle just be any real number here, we go around this circle many times, there's no way to undo that function, right? So, so we say, yeah, so we can't let the angle be all real numbers though, but if we restrict it to some like 2 pi interval, it doesn't need to be 0 to 2 pi. It could be, you know, basically any interval. You get a different branch of the logarithm function. I feel like the standard one should be like 0 to 2 pi, but I know that's not the standard one because I specifically remember that it's not. But for me, the standard one is basically like 0 to 2 pi because that's how I think of angles, right? You think of an angle, you know, you go from 0 to 2 pi, and that's all the way around. So I don't know what an argument of a complex number is. Yeah, so that's what I'm saying. Like we invent these random English words for these things that, you know, why make up another word? It's essentially, it's just the angle that it makes with this positive real axis. So I don't know why they invent a new word for it. It's just an angle. I guess you could probably just call it the angle of the number. I don't know why they have to call it the argument, but mathematicians have to be fancy. We have to make up, you know, words that people don't know. So that you have to be on the in crowd to know it, of course. But yeah, argument of the complex number, it's just basically the angle that it makes with the positive real axis. And then also the other standard word that we create is we have the argument of the number and we have the modulus of the number. But the modulus, again, is just the size. So, and yeah, I don't want to make the notation here too messy, but negative pi to pi. Okay, there we go. That's the standard one. Yeah, so if the standard log, I think we restrict, yeah, Rex is saying that it's from pi to negative pi. So not including the left side, I guess. Oops. Yeah. So here it is a 2 pi interval you see here. And we have to not include, this is actually important, we have to not include one of the endpoints here, or else, you know, the value at that endpoint is actually equal to the value at the other endpoint when you go around the circle. So then it wouldn't be 1 to 1 if you included both of them. So you have to throw one of them out, exactly one. Yeah, so basically you can view every number, right, as some r e to the I theta, but you need to make sure that this number is, the theta is in this range, right? If that's the case, then we can define the log of this. And it's just the normal, you know, exponential log, just the normal log of r. And then we get the angle. So it's plus I times the angle, which is kind of interesting. So yeah, so the number that we get, the real part of it is the natural log of the radius. So in the same sense that like when we multiply complex numbers, the modulus, the size of the number multiplied, here you can kind of think of it similarly where you're taking the log of a complex number, and in terms of the real part you get just the log of the size of the number. So it's just log of r. And then, so why do you get a plus here? So this is because the log, we believe it should add under multiplication. So this should be just log of r, where now r is just a real number, plus log of this e to the I theta, which should cancel out. Okay. So log of e to the I theta, that should just be I theta, right? And log of a real number should just be the normal log. If, you know, any of this should make any sense for real numbers, then I should be able to put a real number in to log, and I should be able, it should just give me the normal log out. or otherwise, what's the point of calling this thing logarithm, right? So any questions about this, guys? So yeah, this was all to answer this question, which we still haven't answered, right? Which is we want to compute the logarithm of 1 minus square root of 3i. So let me write that down. So the question Rex posed in the Discord was, what is the logarithm of this number? So I'm assuming complex logarithm. So what we just talked about. So 1 minus square root of 3i. So the first thing I would do when I look at this is I want to write it in polar coordinates again. In polar coordinates, much simpler to deal with. Actually, I don't even know how to do this without polar coordinates. Is there a way to do that? Yeah, maybe I would need like a Taylor series, right? I would have to write out the Taylor series for this and then somehow plug this in and compute the series, I guess. But that would be annoying, right? Otherwise, yeah, I'm not sure how you would solve this without converting to polar coordinates. Or I guess you just convert to polar coordinates and then, yeah. So, yeah, what is this in polar coordinates? So 1 minus square root of 3i. We want to write this as r e to the I theta. R is the size of the number. This is like viewing this as a point in the plane. The size of the number is just the Euclidean norm. So this is like 1 squared plus 3 squared. It's the, 1 squared plus 3 squared, and then you take the square root. So the size of the number is just 2. Right, square root of 4. Pythagorean theorem. And then what is the angle? So we can hopefully not make a mistake by drawing it out. So it's 1 minus square root of 3i. So 1 unit this way. Maybe it's like right here. That. Yeah, so what is the angle here? So what function do we need to find the angle here? Find the modulus, find the argument, combine for the principal value. Okay. That's essentially what we're doing here, right? Yeah. Yeah, so yeah, if we're finding r, yeah, so actually taking the complex logarithm is essentially equivalent to trying to figure out what are the polar coordinates in r and theta, as long as you restrict theta to the right domain. So here, theta needs to be from negative pi here all the way around to pi. So here we're going to have some negative angle here. And what is that angle? So this angle will be some arctangent, right? So we have x is 1, y is negative square root of 3. And then what is this angle we want? So the picture is, we have negative square root of 3, 1. Oh wait, yeah, and we want to know the angle here. So it's going to be some sort of arctangent type thing, right? Yeah, arctan. But yeah, we need to be careful with the sign because of we need to make sure that the angle that we get, makes sense for this picture. Yeah, arctan. Okay, so so what is it the arctan of? It's the arctan of this over this, right? Can I put this in here? Yeah, and then I always forget like what's the domain of this, so we would have to like think about that for a second. Or we can just plug this in a calculator and yeah, so Rex says this is negative pi over 3. And Was this negative pi over 3 without having to do any sort of, like, you didn't change the negative sign, you just plug this right into the calculator, right? So yeah, this angle should be negative pi over 3, and so that means that we can write this as 2 times e to the negative pi over 3i. Like that. And so if we're wondering what the logarithm of this number is, well, it's just the radius logarithm of the radius. So natural log of 2 plus I times the angle, or in this case minus. Okay. Are there any questions about that? So with this same type of method, we could find the the complex logarithm of any number in rectangular form, except for one number, or actually there's a whole set of numbers that this won't work for. So which numbers can we not plug in here and do this process to? Well, one number we definitely can't plug in is 0. In particular, we can't take the natural log of 0, so that won't work. But there's actually a different problem if you're thinking about this stuff, which is we had to throw out a whole array of numbers, right? So we had to throw out all the numbers that were exact. Oh no, actually, wait. No, we didn't. Never mind. I'm lying. Yeah, I'm lying. I had to think about that for a second. Okay. Yeah, but we still have to throw out 0. Yeah. Yeah, so there's no log of 0, but any other number, we can find a complex log. But the only thing is that this number is not unique, because if we pick a different branch and we don't do this like negative pi to pi restriction, we restrict it some other way to a different branch, then we might get a different answer for this. So this function actually depends on the branch that you pick for it, and that's not super intuitive. It doesn't really happen with inverses of functions in the real case, right? You don't have a multi-valued function usually. Well, I guess it does, because you have like z squared, and you can the inverse is multi-valued as well. So I guess it does happen for the real case, but yeah, and then you also have a restriction of the domain for the real stuff too. So yeah, I guess it does happen in the real case as well. You can use a negative for log. Yeah, so in this case, it's different than the real case. Yeah, you can actually take the log of a negative number here. So if we take the log of negative 2, for instance, what is that? That's actually the log of 2. But now we're going to have, did we include negative pi? No, it was pi. So it would be plus I pi. So the complex logarithm of a negative number in this branch, you just get the natural log of the positive number plus, and now you get basically a shift by this I amount. So you get a natural log of 2 plus I times pi. So what if the real number is negative? What are you talking about? Like this? Did we just answer that? You can use a negative for log. Yeah. So this is how it would work. So log lies on this, the negative numbers lie on this array, which is an angle of pi, and we said that our range was, I believe it was including pi, right? Yeah. So any negative number is going to have an angle of exactly pi. So its logarithm will be, natural log of the number plus I times pi over here. Yeah. Okay, so for Yeah, we already answered this, right? Natural log of 2 minus I times pi over 3. Okay. I think this is a good problem, though, because, yeah, it really shows you what's going on with this. How this log doesn't behave like as well as we would hope in the complex case. Let's see. Do we have any other problems here? Let me check the Discord. Logarithm. Oh, we got a couple more here. Can we do this one? X cubed plus 27 equals 0. You want to find all the complex roots of this? Yeah, let's think about this one. So yeah, this is also related to these to this form r e to the I theta. So a lot of this complex stuff you can boil down to thinking of stuff in polar coordinates. So I recommend like always thinking of things in polar coordinates. So we have, I'm just going to put a z here just because I like z's for complex numbers. Z cubed plus 27, is that it? Yeah. Is 0, and we want to know, if z is a complex number, what are all the possible roots, right? Okay, so here we need a number whose cube is negative 27, right? And remember when we cube a number in polar form, I showed you what happened when we took a number to the 4th power before. But if z is some r to the e I theta, and we take z to the 3rd power, again the radius is just going to be multiplied by itself 3 times, so r to the 3rd power, and the angle is going to add 3 times, so it's going to be e to the 3 I theta. That means that if I want to know which number cubed is going to be negative 27, if I think of it geometrically, that's a number over here, negative x-axis, negative 27. I need a number whose angle is basically like a third of this, so that when I go this way, I do it twice, and then I do it 3 times. I'm going to end up here. And I need a number whose cube is 27 in size, so that's going to be the cube root of 27. 3 times 3 times 3 is 27, so the cube root is 3. So basically this r is forced to be of size 3, or else this won't work, because r cubed has to be 27. And the angle needs to add 3 times to be pi. So 3 theta needs to be pi, so that means that pi needs to be pi over 3. So r needs to be cube root of 27, theta needs to be pi over 3, and then we're good. But that's only one of the roots. You can actually get here 3 different ways. So you can start here, and you can go kind of like boop, or sorry, this is, z squared would be somewhere over here, and then z cubed is over here. So you get this like jumping. This is one root, but we have other roots. So here, I guess maybe I shouldn't say implies. This is like one possible solution. But there's other possible solutions, which is because this range, I can start here and I can go around. What is it? Yeah, so I'll ask the chat, what's an angle where 3 times the angle is equal to pi, but where it's like mod 2 pi, or mod pi. So anytime I go above pi, right, it kind of resets back to negative pi, right? And so there's actually 3 solutions here, I believe. One of the solutions we found is if theta is pi over 3, then obviously if I go 3 times around, then I'm at pi. But What else works? Let's see. Probably something like down here, maybe. Has anyone worked this out yet? So pi over 3 works. That's the obvious answer. That's like here. Then let's think about it. So 3 theta is pi. So let's think. Maybe theta could be like, maybe, what is this? Negative, why can't I do this? 5 pi over 3? What is that? Negative 4 pi over 3? I don't think that works though. No, if I do 3 of those, then I'm at negative 4 pi, so that's not right. Because negative 4 pi would be here. So, yeah, has anyone figured this one out? I guess I'll just wait for the chat a little bit. Okay, Rex says 2k pi over 3. 2k pi over 3? I don't think, yeah, so if it's 2k pi over 3, then it doesn't work. Because then when I multiply by 3, then I get a multiple of 2 pi, which would mean I'm over here. When I multiply the number by itself 3 times, I want to end up here. So like this angle works pi over 3, then I'm at 2 pi over 3, then I'm at pi. Snake King says pi over 3, pi, and 5 pi over 3. Okay, let's try those. That sounds like a good attempt. So if, yeah, so pi over 3, we already know that works, right? Times 3. This is pi. We're good. Pi, when I multiply by 3, I get 3 pi, but if I'm thinking mod this system where, you know, I need to restrict between negative pi to pi, then 3 pi is actually equivalent to pi. So this is pi, all right here, like mod, I'll just write our system. I don't want to explain the like modulus stuff, but in terms of an angle that's restricted between negative pi and pi, then 3 pi is equivalent to pi, right? So there's like equivalence classes here, mod 2 pi, or, you know, mod this 2 pi restriction, and 3 pi is equivalent to pi, and that's what we want because we want the angle to be pi. That's where negative 27 lies. It has an angle, an argument of pi, so that's good. And then the last one, we have 5 pi over 3. And again, let's see, I think it works. So 3 pi, yeah. So then when we multiply by 3, so we get 3 of these angles, I get 5 pi, which is equivalent to pi again. So any odd multiple of pi, I'm going to end up here. Any even multiple of pi, I'm going to end up on the positive side. Okay, so those are our 3 roots, and there's actually a theorem in for complex analysis that says any polynomial with complex coefficients has at most 3 roots. We just found 3 different roots, so this must be all of them. So yeah, so the 3 roots are where r is the cube root of 27, which is 3, right? So all of the roots are, maybe we can just write them. Yeah, so the 3 roots are 3 e to the pi over 3, 3 e to the pi, to the 5 pi over 3. Oh, wait. That's not even on our range, right? That's actually... That should be... Oh, I guess it doesn't matter. But, yeah. What is this, though? This is negative 2/3? Pi I? Forgot the i's. Okay, so those are our 3 roots, and then... of course, this one... if we wanted to write it the other way, what is this? Okay, yeah, so this is like 3... Ugh, I forget my trigonometry. What's pi over 3? That's cosine is 1/2, right? So 3/2 plus square root of 3 over 2. 3 square root of 3 over 2 I think. Which is, this is just Euler formula, right? I'm doing cosine of this angle and sine of this angle and then multiplying by 3. I was taught by my school to not use negative angles. Oh, yeah, I know. This is just what we were doing before. Sorry. Yeah, I mean, of course it doesn't matter. Like, mod 2 pi, as long as they're the same, should be good. But, yeah. Yeah, I'm just sticking with the convention we were doing with the logarithms before. So, yeah, I don't know. I think this is fine. So then, yeah, this is just a negative number. So this is negative 3. Because an angle of pi, e to the pi I, right? This is the famous formula. E to the pi I is negative 1, right? So 3 times negative 1 is negative 3. And then here we want cosine of this angle again. This will be negative 1/2. So this will be negative 3/2. Wait, that's wrong. Oops. What is this? 4? No, 5? Yeah. Wait. No, I'm doing this wrong. What was the angle again here? I think I did this last one wrong. We'll figure this last one out in a second. What's the comments? How do you get negative 2 over 3 times pi? Which one? Where are we looking? Did I just erase it? Right, so we wanted an angle whose 3 times the angle was, pi or some odd multiple of pi. So pi over 3, we multiply by 3, we get pi. Pi, we multiply by 3, we get an odd multiple of pi. And then I think it was like, what was the last one people said? So it was 3 e to the 5? 5 pi over 3, right? That was it? Yeah, I think that was the other one. Right, okay. Yeah, now I'm messing myself up, sorry. So what is the cosine of this? That's what I want to know. Cosine of this angle, it's 2/3 of the way up, so it should be like, wait, I don't know why I'm confusing myself so much. So we have one full angle, or 1/2 of a circle, and then 2/3 of another. Oh, okay, okay. So the cosine is 1/2, I think, right? So 3/2 minus 3 square root of 3 over 2i, I think. Is that right? Or did I mess up the angle? Feels backwards. Oh no, if I switch it, then I'm going to get the negative of it. So it's... Okay. Is that right? Okay, it's right. Right, yeah. So what was the whole point of this, just to recap and not confuse everyone? We wanted a number where the size of the radius cubed gave us a radius of 27, because we knew that the number negative 27 has a radius of 27. It's just that the argument is of a pi argument, right? So the radius has to be size 3, and then we just need 3 different angles here in the complex plane that when you do 3 of them, you end up with, some odd multiple of pi, which means you'll end up in the negative real axis. So we chose pi over 3 because when we multiply by 3, pi over 3 becomes an angle of pi. Pi, when you multiply by 3, becomes 3 pi, which is an odd multiple, and then 5 pi over 3 becomes 5 pi, which is also an odd multiple. So the cosine, why the cosine though? Yeah, so this is the Euler formula. So e to the I pi, e to some angle times I is this is cosine of the angle plus I sine of the angle. So this is the Euler formula. Right, so that says that I can convert from these polar coordinate form to rectangular coordinates using this formula, and I just need to know what's the cosine of the angle, what's the sine of the angle, and then just multiply everything by 3. So that's how I got this, and then this one was actually just on the negative real axis. So this one was just negative 3. This is our normal, cube root of negative 27. This is what we normally think of. But in the complex plane, we actually get 2 other roots. So this is a complex root. This is a complex root that are not real. This is the only real root of negative 27. Yn plus 1 equals yn plus h. Oh, what are we saying here? Kotabot? Are you talking about the Euler method? Okay, yeah. Sorry, I thought the board was all messed up. That looks good. Okay. Let's see. You need to give me a particular problem. I'm not prepared to just wing up a lecture on Euler's method real quick. We can go over a particular problem if you have one that you want to look at, but okay, so this was finding the cube roots of negative 27. So we wanted to find all numbers where z cubed was negative 27. We found them. One of them was real. The other 2 were complex. Right. I think we're good on this one. Any questions about this or Euler's formula here? Going pretty long today. I'm getting pretty tired already. Oh, okay. So what do we want to do for the rest? 45 minutes or so. Yeah, check the Discord. Putting any problems in the Discord. I think, what do we have here now? Oh, we have this one also. X to the fourth minus square root of 8 plus I square root of 8 equals 0. That looks ugly. Huh. I'll think about it. Sorry, I didn't check if there are any questions. Nope, okay. Okay, yeah, so I can ponder this other question. Yeah, think about it. X to the fourth. I'm going to convert it to Z again just because I can't have my complex numbers be X's. They just can't be. I don't know why. Okay, so it is a complex polynomial. We want to find the roots of it. It's complex because this is like the zero coefficient, right? It's just a complex number. Okay, yeah, so this is similar to the last one, right? Yeah, so Z to the fourth is basically this cube root of 8 plus, of times, what is that, 1 minus I? So yeah, similarly, we want to basically write this number as in polar form, and then we want to try to figure out, again, what angle, when I do it 4 times, I'm going to get this number. And what does the modulus of the number need to be when I raise it to the 4th power and I get the modulus of this number? The thing is that this number doesn't have modulus 1, so yeah, I need to write this in polar form first. How do I think of this in polar form? I can always divide out the modulus here, which is square root of 2. So basically like multiply top and bottom by square root of 2. So square root of 2 times square root of 8 times 1 minus I over square root of 2. Square root of 8 is 2 square root of 2, so this is 2 times 2, which is 4. So it's 4 times 1 minus I over root 2. And this number on the right, the reason I did this, the reason I'm divided by square root of 2 was because now this number is on the unit circle. It has size 1, it's modulus 1. So I can write this number as like e to the I theta something. So this is 4 e to the I. So this is, I need to think like, this is 1 minus I, so it's here. So the angle is either negative pi over 2, or if you think positively, it's 3 pi, what is that? 4, 8. Can't do math all of a sudden. 4 pi over 4, 3 more, 7 pi over 4. Yeah. Okay. Yeah. So, yeah, and we want to know what number to the 4th power is this, right? So that's the key right here. Okay, so if a number to the 4th power is 4, then I know that the size of that number has to be square root of 2. So if z is equal to r e to the I theta, then we know that r is equal to square root of 2, because its 4th power is 4. And we have a bunch of different angles we can have here in the complex plane. We just need that when I do the angle 4 times, or when I multiply the angle by itself 4 times, or sorry, when I multiply the angle by 4, then it needs to be 7 pi over 4. So 4 times the angle needs to be 7 pi over 4. So the like principal value, I guess, is that what it's called? This is 7 pi over 16. Okay. Yes. Oh, 7 pi over 4. Right. 7 pi over 4 here. Oh, okay. Yeah. You're just talking about this snake, this 7 pi over 4 here. So yeah. Now again. So if 4 times the angle is 7 pi over 4, then the angle must have been 7 pi over 16, or it could be, one of these other multiples. So, oh, I think Rex was trying to hint me at what I was supposed to say before, but we'll go more into this stuff once I get more formally into it. But yeah, this is only one of the answers, right? But we have 4 roots. It's a complex polynomial of degree 4. It has 4 different solutions usually. So this is one of the solutions. So we'll call this one Z1, I guess. This is square root of 2 e to the I 7 pi over 16. But then there's also Z2, which has same size, square root of 2, and e to the what? So what are some of the other ones? Anyone in the chat can answer. And this is only because I don't want to do the problem. So yeah, who can find the other angles here? And maybe you can even explain to chat, how you got the answer. Or like maybe what's a systematic way that you could always get the answer for a problem like this. Just keep on piling or piling. 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 So 7 pi over 16 works. Yeah, so we want the resulting angle to either be 7 pi over 4, or it can be a multiple of 2 pi added to 7 pi over 4. So it could be like 7 pi over 4 plus 2 pi, or 7 pi over 4 plus 4 pi, or 7 pi over 4 plus 6 pi, something like that. So, yeah, that's basically it. I guess we're not doing 24 hours this time. No, nope. No, honestly, I think 24 hours is too long. I think that's a little dangerous. I felt like really tired after, like extremely tired. Okay, so Snake King is saying 15 pi over 16, 23 over 16, 31 over 16. And then he's giving us a formula which says 7 pi over 4 plus k times 2 pi, and then on that all over 4. Right. So that's the point. That's the perfect point. Yeah, we can keep adding multiples of 2 pi to 7 pi over 4, and then we can find an angle who when we multiply by 4 is equal to that, extra angle, where we take 7 pi over 4 and we add some multiple of 2 pi to it. So yeah, let me write that at the top. So the general formula is we have 7 pi over 4. Then we can add some k multiple of 2 pi. And then we want to divide by 4. So if k is 0, then we get our original answer, z1. If k is equal to 1, then I'm guessing we get 23 over 16. Yeah. So this would be like 23 over 16. Is that right? Yeah, someone check this. I think it's right, but Right, and then you just keep doing this. So just basically plug in different values of k here. So k is equal to 0, 1, 2, and 3. And that gives us all the solutions. So those are, and then maybe you should just check that these are actually different numbers. So try to, maybe you can do this at home. Try to write all of these 4 numbers in rectangular coordinates. You know, you can use a calculator. So actually, you don't even need a calculator for these angles. Actually, do you? Yeah, maybe you need a calculator, but try to write these in rectangular form. Maybe just use a couple decimal places for the cosine and the sine of these, right? Because once you have an angle, I think like 7 pi over 16 might not be one you can write down unless you look it up on Wikipedia or something. I think it's like a square root of a square root or something, but it's, yeah. Or you could just write it as, you know, first 2 decimals of cosines, something like that. Okay, any questions? And then in general, you can do all of these problems this way. So if you want to have like z to some power is equal to some number, as long as you can write it in polar form, then you're just going to be finding whatever the nth root of the modulus is, and you're going to be doing this thing with the angles where you're adding some multiple of 2 pi, and then you're finding new angles that when you multiply them by 4, you get 7 pi over 4, but again, mod this 2 pi. Trying to think. What else do we have? Do we have any more Discord problems? Okay, so that was that one. Let's see. Trying to maybe make up a problem. Wait, was there another good complex one in there? Thank you for going over these again. I was used to solving these without Euler's formula, which it just seems a lot easier. Yeah. No problem. This is definitely the way to think about this stuff for sure. What was I just thinking about? Okay, so yeah, let me look at these other complex problems on here if there's anything good. Okay, we can probably do this one just quickly. This e to the 1 plus pi over 3i. So yeah, a lot of these problems will involve converting between polar and rectangular coordinates. So anytime you see like an e to a complex number problem like this, really you want to internalize it as you're converting from polar to rectangular. So e to the 1 plus pi over 3 I. Well, I guess you're not really converting, but well, if you rewrite it as like e to the 1 times e to the pi over 3, then now it looks like you're converting from polar to rectangular, right? So here now the radius of this number is actually e to the 1, so it's actually e. So it's the radius of the number is e. And the angle is pi over 3. So this is a cosine of pi over 3 is 1/2. And no, sorry. Square root of 3 over 2 plus 1/2 I. And yeah, now we're good. We can just distribute the e. So it's e times square root of 3 over 2 plus e over 2i. And that is our number here, this complex number, this complex exponential, written in polar form, in rectangular form. So here's the real part plus imaginary part times I. Okay, so that's, yeah, real quick one there. Let's see, my battery's actually starting to die a little bit. Maybe I might have to end a little early, but let's see, are there any good ones in here that we haven't looked at yet? Yeah, I'm not sure I understand your question about the complex potential one. says write the complex potential of a vector field having a source at 0, 0 and another source at 0, 1. I'm not sure I understand what that means. Yeah, I'm a little confused about that one. I could do the residue one, but I feel like that's too advanced for us to do right now. I could talk about the power series, I guess. Yeah, power series is probably one. Okay, yeah, let's look at this power series. So it says find the radius of convergence of this power series. So power series for complex numbers are very, very interesting. In fact, power series, if they converge on some radius of convergence, then they actually converge to a complex analytic function automatically. So there's sort of, you can think of them as sort of equivalent. Any analytic function or any holomorphic function, complex differentiable, these are all like synonyms. They can all be written as some Taylor series. And the Taylor series will, have some radius of convergence wherever, basically it has some radius of convergence up until it hits some problem where it can't converge. For instance, like you have the Taylor series 1 plus z squared forever, right? So this is like your geometric series. Z to the I. And actually ran out of water. I have nothing down here. Sorry. Well, that's what happens when you do a 4-hour stream. You eventually run out of water. But yeah, so this Taylor series, we want to think about like what's the radius of convergence and what function does this converge to? So we know from like one variable calculus that this converges to a function 1 over 1 minus z. And this function isn't defined at z equals 1, right? So this equals this, at least where it converges. Right, so maybe this should have like an asterisk next to it. It doesn't really equal it, but at least all the values where this converges, it equals this. Okay? But the problem is that it's not defined at z equals 1, right? Because I can't plug in 1. And in fact, numbers that are getting closer to 1, this is blowing up. So this Taylor series has like a natural problem with 1. I can't plug in 1. If I plug in 1 here, I get 1 plus 1 plus 1. It definitely doesn't converge, right? It goes to infinity. So in fact, this Taylor series has a problem at 1, and in fact, the radius of convergence of this is 1. So I can plug in any number that has a radius of smaller than 1 into here, and I get a convergent Taylor series. So I can plug in like 1, let's say I over 2, for instance. I over 2 is a number that I'm allowed to plug in here, and I'll get some 1 over 1 minus I over 2. And then you can simplify whatever this is. But yeah, and then this would be, so this should equal I over 2. This should equal 1 plus I over 2 plus I over 2 squared. And you keep doing that forever, you should just get this number, which is like 1 over 2 minus 2I over 2, which is 2 over 2 minus 2I, which is 2 plus 2, 4 is 8. 2 plus 2I over 8. Yeah. Which is 4 over 8, which is 1/2, which is plus 1/2 I. Okay. Right. So basically all of that math to show that if you took I over 2, so 1 plus I over 2 plus I over 2 squared plus I over 2 cubed, and you kept doing that forever, it should converge to 1/2 plus 1/2 I. Because it's equal to this on, wherever it converges, and it should converge in a radius of 1, so as long as I plug in a number that has a modulus of less than 1, it should converge. Okay, so I haven't proved anything here. I'm not proving that the radius is 1, but I'm giving you some sort of intuition for why the radius might be 1, and that's because it's equal to this function where it's defined, and this function has a problem. I can't plug in z equals 1. So it naturally has this boundary where we know it's going to blow up when I get close to 1, and therefore it sort of prevents it from converging anywhere else in the plane that's of modulus away more than 1, or 1 or more. That seems wrong. 2 over 2 minus I. Did I do it wrong? What's wrong about it? Is it wrong from here? Okay, wait. So here to here looks good. Here to here looks good. So I'm multiplying top and bottom by 2 plus 2i. That's to get the modulus on the bottom, which is going to be 2 squared plus 2 squared, which is 4 plus 4, which is 8. 2 times 2 plus 2i. Just distribute it, divide by 8. I think it's right. 2 over 2 minus I. Can you tell me where it's wrong? I think it's correct. Excuse me. Never mind. I think I understood wrong. Okay. As long as we're okay here. Yeah, I wrote it a little bit messy. I'm going kind of like this way. The sequence of the steps is this way. Okay. Right, so radius of convergence is 1. So this problem in the Wednesday submissions that Rex sent in says find the radius of convergence of this particular power series. And this one is very much related to the one we just looked at. It's just that we're only adding 2/3 of z to the n. Assuming it's 0 to infinity, right? Yeah. Okay, so if we want to know what's the radius of convergence of this, well, this is basically very, very, very similar to the Taylor series I just erased. In fact, if we do a change of coordinates and I rewrite this as like w is 3/2 z, then switching coordinates, that would mean that this is actually just w to the n, right? And this we know is equal to 1 over 1 minus w. As long as w is less than 1 in absolute value, it has a radius of convergence of 1, right? And if w is in this radius of convergence, then we know that since w is 3/2 of z, then 3/2 z needs to be less than 1 in modulus and less than 0. And that means that z, the modulus, you can it's multiplicative, so you can pull out the 3/2. So that means that 3/2 z needs to be less than 1 and bigger than 0. And then you can put the 3/2 over here, so divide by 3/2, so you get 2/3. So basically z has to be between 2/3 and 0. So our radius of convergence for this Taylor series, radius is, we can usually write it as like a capital R. This is 2/3. Oh wait, is that wrong? I think that's wrong. What did I do wrong? W needs to be less than 1. Oh, oops. Oh, this isn't W. This is, yeah. Oops. Wait. What did I do here? W is 3/2, so got a dog upstairs. 2/3 W is Z. Or I wanted 2/3 Z to be W. That's what I wanted. Right. Yeah, so this 3/2 should be a 2/3. Oops. Okay, so 2/3. Yeah, it didn't seem right. Okay, then we divide by 2/3, we get 3/2. You wrote it upside, but math is correct, 2/3. Yeah. Also, I want my coffee dehydration I redeemed, but I think you didn't notice. Yeah, no, I noticed it. I just don't have any water here. we're too deep into the stream. You gotta catch me earlier to have beverages. Okay, you wrote it upside down, but math is correct, 2/3. Okay. Yeah, so basically radius of convergence needs to be 3/2. Okay. Which makes sense because essentially this is just a shifted Taylor series, right? This is just the Taylor series for W to the N as long as we change coordinates, right? We just need to multiply scale by this 2/3 factor. So if we scale by 2/3, if we're scaling by 2/3, then the radius in the scaled coordinates gets slightly bigger, right? So 3/2. Because 3/2 times 2/3 is just 1. So, yeah, basically if you scale down, the radius gets larger because, in the scaled down coordinates, the radius becomes bigger. It makes sense. Just gotta kind of reason through it a little bit. Yeah, I think I'm really running out of battery here. Oh, I don't want it to crash too much. All right, I got 13% battery here. Are there any last minute problems we have to go over? Or I might end it soon, just for the sake of battery. Let's see, are there any good ones? So the only ones we didn't really go over in the Wednesday is the residue one. So we'll get more formal into the complex analysis. We'll start the introduction formally on Friday, and then we'll get more into the complex stuff, the more advanced complex topics later, where we'll talk about like these residue theorem type problems. Taking integrals, complex integrals is important as well. Integrating complex differentiable functions. There's a fundamental theorem of calculus that's very similar to the way that it works for real functions. So yeah, a lot of these topics we'll eventually get to these. I don't know if we'll be able to get there maybe in a couple of weeks. We'll be doing like Cauchy's theorem and a bunch of Cauchy's formula, stuff like that. So yeah, integrals of complex functions, taking derivatives of complex functions, and different polar form. A lot of the stuff that we did today is kind of more of your introduction to calculating with this new dimension of numbers. Yeah, no problem, Rex. Appreciate you guys stopping by. Don't see any new problems here, and I am running out of battery, so I may have to end it here. Yeah, nothing in here. Oh wait, did we get one in the general? Okay, no. Yeah, so I think this is a good place to end it. We did a lot of problems today. I think we did at least like maybe 5 to 10 problems. So that's pretty good. And I'll put the video on YouTube so you can find it if you didn't see everything today. If you're just tuning in now, you can find the video on the YouTube here, which I'll put in the chat. And you can find the Discord. I do tutoring. So here's the link for tutoring. And I can tutor in, linear algebra, most math subjects. So linear algebra, probability, complex analysis, real analysis, calculus, multivariable calculus, anything like that. So definitely contact me if you need any sort of tutoring. I can do undergraduate, graduate, doesn't really matter. And check out the YouTube as well. And join the Discord. All right, so let's find somebody to raid. Let me